Hi students, good morning. In our yesterday class, we are discussing about complete crystallographic methods. These methods are used to determine the structure of the given crystal. So in every method, we are mainly calculating the D value. What is the interplanar distance? Depending on interplanar distance, you can calculate the lattice constant value. So once lattice constant value is calculated, next we are calculating number of lattice points per unit cell. Depending on number of lattice points per unit cell, you can determine the structure of the cell is either primitive or face-centered or body-centered cubic structure. In this way, crystallographic methods are very useful to determine the crystal. Especially out of four, one method is mainly used only for powder form crystal. Why you are using the powder form crystal is nothing but powder form crystal having lot of tiny particles. Tiny is nothing but very small particles. That depending on the small particle structure, you must follow the one and only method, that is called as powder photographic method. Except powder photographic method, remaining three. What are those? Lay method, second one X-ray Bragg spectrometer, and third one is rotating crystal method. These three methods are mainly used to determine the structure of the crystal. Structure of the crystal which is in the solid form, other than the powder form, nothing but other than the amorphous form. Other than the amorphous form is nothing but to determine the crystals, that crystal should be crystalline crystal. So the crystalline crystal structure can be determined by using three crystallographic methods, that is lab method, second one is X-ray Bragg spectrometer, third one is rotating crystal method. These three methods are used to determine the crystal structure. That crystal should be crystalline structure. Crystalline structure is nothing but the atoms or lattice points are arranged in a orderly. Particularly, you can arrange the atoms in orderly. Then the crystal is called as crystalline crystal. Out of going to the crystalline crystal completed, after that you can go to the amorphous. Those are called as non-crystalline crystals. That non-crystalline crystals can be, that non-crystalline crystal is nothing but amorphous solids. That amorphous solid structure can be determined by using complete only one method, that is called as powder photographic method. That is the crystalline methods to determine the crystal structure. After completion of crystal structures determination, and the next and very important topic is called as diffraction intensity. Diffraction intensity. So what is intensity? According to your lower class level, intensity is represented by capital I. This I value can be calculated by using intensity of waves or light is always be directly proportional to square of the amplitude. I is always be proportional to square of the amplitude. Here diffraction. Diffraction simply is nothing but bending of light. According to diffraction pattern, we are following the diffraction condition. What is the diffraction condition? The diffraction condition is 2d sin theta is equal to n lambda. For this diffraction pattern or diffraction condition is clearly explained by based on which rays are used. We are using particularly X-rays. Why you are using X-rays? These X-rays wavelength is lambda value exactly is equal to or approximately equal to 1 angstrom. Based on that lambda value, we are using the X-rays. Based on this X-rays are inciding on the crystal lattice planes, those are diffracted. Then diffracted rays obeys the condition is called as Bragg's condition or Bragg's law, that is called as 2d sin theta is equal to n lambda. This is the diffraction intensity. This diffraction intensity can be derived. So you can derive the formula for diffraction intensity. So this diffraction intensity is completely different from diffracted X-rays. Completely different from diffracted X-rays. Diffracted X-rays. Why is completely different from diffracted X-rays? Generally, you have the one crystal. Crystal is nothing but combination or periodical arrangement of lattice points. So otherwise, the combination of lattice planes. You can incident on the X-ray like this at a particular angle of incidence. Here the angle is theta. It may be diffracted like this. It may be diffracted. So the incident wavelength can be taken as lambda. So here lambda value, otherwise theta value must be balanced. They can obey the diffraction condition, that is 2d sin theta is equal to L lambda. So this diffraction pattern or condition is obeyed at a particular wavelength and at a particular glancing angle. So at every angle of X-rays or inciding on the crystal does not obey the Bragg's condition. Does not obey the Bragg's condition. That Bragg's condition obeys at a particular angle of incidence, at a particular angle of glancing. So that particular angle, otherwise based on the incident wavelength. So these main two factors, based on these two factors, the diffraction condition is obeyed. Once the diffraction condition is obeyed, then at that condition, diffraction pattern is observed. The diffraction pattern is observed. Based on diffraction pattern, you can determine the structure of the crystal. So at every angle does not obey the diffraction pattern. That every angle or at every wavelength of the X-rays does not obey the diffraction pattern. But the crystallographic method must obey the diffraction method. Diffraction method is nothing but 2d sin theta is equal to n lambda must obey. That condition diffraction is must and should be cleared. So the diffraction is obeys is nothing but 2d sin theta is equal to n lambda. This equation is not always be satisfied, because this equation is satisfied based on theta and lambda. At a particular lambda and at a particular glancing angle, the diffraction pattern is observed. So at every angle does not obey the diffraction condition. Why? At every condition does not obeys the diffraction condition. But diffraction is occurred, but it is necessary to follow the diffraction condition. It is necessary to obey the diffraction condition, that is 2d sin theta is equal to n lambda. Why it is not necessary, or why it is not obey the diffraction pattern? It is mainly depending on two primary properties of the crystal. Properties of the crystal. Actually, diffraction occurs at the condition, diffraction pattern must be obeyed. That condition is 2d sin theta is called n lambda. Once the diffraction condition is not obeyed, that why the diffraction condition is not obeyed, that is mainly depending on two primary properties of the crystal. What are those? The first one is atomic. The first one is atomic scattering. Atomic scattering factor of each atom in the crystal. That is the first factor of does not obey the diffraction method. That is atomic scattering factor of each atom in the crystal. And second one is position of the atom. Position of the atom in each unit cell. In each unit cell in the crystal. These are two primary factors based on why diffraction pattern does not obey. The diffraction pattern does not obey mainly depending on two factors. One is atomic scattering factor of each atom in the crystal. Second one is position of the atom in each unit cell of the crystal. Why you are taking the position? According to your derive the 2d sin theta is equal to n lambda, particularly the X-rays are inciding on the lattice planes like this. You are inciding on the lattice points. Based on lattice points, you can inciding on the lattice point, the light ray is diffracted like this. So at this condition you can derive the 2D sin theta is equal to N lambda. The instant X-rays or light rays are inciding on the particularly on the lattice point. Suppose you are not inciding on lattice point like this. Here two lattice points are there. You are inciding on the X-ray like this. At this condition, diffraction pattern is not obeyed or diffraction is not occurred at this condition. So, diffraction pattern or diffraction condition is obeyed. The incident rays must be inciding on the lattice points. On that way, position of the atom on each cell of the unit cell must be depending. So, that's why the main two primary properties of the crystals does not obey the diffraction pattern is, first one is atomic scattering factor of each atom in the crystal. Second one is position of the atom in the each unit cell of the crystal. That is the major two factors based on the why diffraction is not obeyed at every condition. So, diffraction is obeyed mainly based on two factors. One is glancing angle, second one is variation of lambda. That is the one factor. Other does not depending on lambda and theta. Why diffraction is not occurred? Mainly two conditions. Those are, one is atomic scattering factor, second one is position of the atom in the unit cell of every atom. Position of the atoms in the each unit cell. That is two factors mainly depending on. So this diffraction pattern is explained, or the diffraction intensity is mainly explained on the atomic scattering factor. This diffraction intensity is mainly explained on the atomic scattering factor. Atomic scattering factor. This is also simply called as form factor, which is represented by small f. This diffraction intensity mainly explained on the atomic scattering factor or particularly form factor. Why it is used? What is it is? What is the name of atomic scattering factor? Here scattering. So you are inciding on the X-ray, how much amount of is scattered? Like this. Suppose I have the one lattice point plane. I am inciding on the X-ray like this. Inciding on the X-ray. This I am taking 100% of intensity inciding on the X-ray. How much amount is scattered? Like a 70%, otherwise 80%, only 10% amount of intensity is scattered. That how much amount of is scattered is explained on the basis of atomic scattering factor, otherwise which is simply called as form factor. Nothing but it is the measure of. It is the measure. It is the measure of efficiency. It is the measure of efficiency of an atom in scattering of scattering of the atom. Scattering of the atom by X-rays. This is the main function of scattering factor. Why the scattering factor is used? That scattering factor value gives the measurement, which gives the measurement. What the measurement? Which gives the efficiency of the atom, particularly which gives the efficiency. How much amount of rays are scattered. That efficiency can be given by the factor is called as form factor or atomic scattering factor. So, suppose you can take the one atom in the crystal or lattice plane. You can incident on the X-rays like this. X-ray, 100% of intensity. This X-ray is diffracted like this. How much amount of X-ray is diffracted? 80% of X-ray is diffracted. That 80% value gives the value that particularly X-ray, that is particularly atomic scattering factor gives the how much amount of ray is scattered. That amount can be measured by using the atomic scattering factor. The atomic scattering factor or form factor can be defined as this atomic scattering factor, otherwise form factor. Atomic scattering factor, otherwise form factor, which is represented by small f, can be defined as the ratio of amplitude of scattered, the amplitude of scattered by the atom to the amplitude of scattered by the electron. That ratio gives the form factor. Here the ratio of form factor can be defined as the ratio of amplitude of the scattered by the atom to the amplitude of the scattered by the electron. So what is that? So you can take one atom like this. This is atom. First you can instanting on the X-rays. How much amount is diffracted? That is, amplitude can be taken as A1 by using X-rays. At the same atom, you can instanting on the some electron beam. This electron beam is also diffracted like this. That amplitude can be taken as A2. So, that form factor can be represented by A1 by A2. A1 is diffracted X-rays with an amplitude A1. A2 is diffracted electron beam with an amplitude A2. So, there is the units are there. Both amplitude and amplitude. Centimeter by centimeter cancel. Meter by meter cancel. So, there is no units. The form factor has no units. They have the dimensional formula. There is no dimensional formula. There is no dimensional formula is nothing but m power 0, L power 0, T power 0. So particularly the form factor can be defined as the amplitude of scattered by the rays by the atom to the amplitude of the scattered rays by the electron. That ratio gives the form factor. This ratio value mainly explains what's the mainly which can measure the efficiency of the atom, how much amount of rays or X-rays are diffracted. That amount of efficiency can be explained by using form factor. So this is the main factor to determine intensity of diffracted rays. The intensity of diffracted rays. Already I told that intensity in lower classes already known. I value is always P proportional to A square. Sometimes you can take I is equal to A square. So intensity can be calculated by using square of the amplitude. So there is no dimensional formula, that is m power 0, L power 0, T power 0. So this form factor value mainly explain the measure of efficiency of the atoms scattered by the atoms of X-rays. So how much amount of X-rays are diffracted, that is can be explained by using the form factor value. So this form factor value can be calculated by using any crystal. Suppose according to for form factor value calculation, for easy calculation point of view, we will consider the crystal atoms must be in point size. That means you can consider one atom like this. This is complete atom in the crystal, one of the atom in the crystal. this complete atom can be considered as point size. That is, so that is this atom is represented by point. Another atom is represented by point. I think but you are considering on the crystal is the combination of lattice points. So the atoms must be considered as the point size. So the total atom is considered as a very tiny size. So that very tiny size point of view, you are calculate the form factor value always be equal to its atomic number. Its atomic number of the element or atom. So the F value must be equal to atomic number is represented by Z. So small f value always be equal to Z. At what condition? The crystal is considered as the combination of atoms. Those atoms must be considered as very small in size, that particularly point in size. On that way, the form factor value always be equal to atomic number. Always be equal to atomic number. That is, so in this way, the scattered ray and incident ray have the some phase difference. The scattered ray and incident ray has some phase difference. That phase difference can be taken as some pi naught. In some textbooks, it can be represented by delta pi also. Here I am considering as the phase difference between scattered and incident X-rays have pi naught. So in some textbooks, you are taking the delta pi also. So the pi naught is the phase difference between the scattered X-rays. So on that way, you are calculating the pi naught value. For this case, I am considering one crystal like this. Suppose I am considering the crystal. This is the crystal. So clearly you can draw it. You can consider one crystal. This can be crystal. So I am taking one lattice plane. So this lattice plane is represented by HKL. What are HKL? HKL are called as Miller indices. HKL. H represent along the X direction, K represent Y direction, L represent Z direction. This plane, the plane indication. So I am taking one lattice plane. According to this complete volume, I am showing only small volume. Here I am considering small volume that can be taken as dV. So this is a point sized atom. I am inserting one ray on the lattice point. In this direction. It is represented by K bar. This K bar is diffracted. Thus diffracted is observed with respect to volume in this direction. This can be taken as R bar. Suppose this light ray is diffracted like this, making an angle theta. This can be taken as K bar. Suppose it is diffracted another ray in this direction. This can be taken as K dash bar. This is K bar and this is K dash bar, which is also diffracted an angle theta. So the difference between K to K dash, this is can be taken as delta K bar. Delta K bar, that is K dash R bar minus K R bar, which is called as delta K into R bar. That is called as, this delta K can be called as path difference. That is called as path difference. K dash and K. That is called as path difference. First, what you want to calculate? We want to calculate particularly phase difference. We want to calculate phase difference. But here calculating the path difference. How much path difference is known? Delta K value is equal to K dash into R bar. Otherwise K bar dash R bar. So we want to calculate phase difference. What is the main relation between path difference and phase difference? Which is came in the intermediate second year. Otherwise in ray optics degree second year optics paper. Otherwise in modern physics fourth paper. So in degree level or intermediate level, the relation between path difference and phase difference always be written as path difference delta pi value is equal to 2 pi by lambda into delta x, which is the best relation between the phase and path relation. Here we are taking the phase difference is pi naught. So I am taking pi naught is equal to 2 pi by lambda into pi delta x path difference, which is can be taken as delta k bar into r bar. Delta k bar into r bar. This is can be taken as delta k bar. This is can be taken as delta k bar. So the phase difference between the scattered X-rays can be taken as delta pi, or pi naught can be taken as delta k bar. Delta k bar. So here in this condition having the path difference and phase difference. Suppose the phase angle is existed. The phase angle is existed out of phase. Out of phase. Nothing but pi naught is existed out of phase. This out of phase point of view, the density factor value, the density of the element can be represented as rho of r bar into dv bar. dv bar, otherwise dv. This is the density factor value. Here rho of r is nothing but here rho of r bar is nothing but electron charge density, and dV is nothing but unit volume. So that is called as rho of r bar into dV bar. Suppose this phase angle is existed out of phase. This form factor value for small volume can be represented as dF value. The form factor value dF value can be written as rho of r bar into dV into e power I into pi naught. According to pi naught, you should represent the delta k. So this dF value, small form factor value, is rho of r bar into dV into e power I into delta k. This delta k is can be represented as rho of r bar into dV into e power I into k bar dot r bar. This is small form factor value in the volume of dV. The dV value is very small volume. This value is calculated. This is small form factor value. Form factor value is measured value of scattered by the X-rays. So this equation is on integrating on both sides. We get integration of dF is equal to integration of rho of r bar into dV into e power I k bar into r bar. Integration of small form factor is equal to large form factor value f is equal to integral of rho of r bar into e power I into k bar into r bar into dv. This is the form factor value. This is the form factor value. That value must be calculated. Here integration with respect to volume integration. Volume integration nothing but you can integrate the entire term by 3 integration with respect to length, with respect to area, with respect to volume. Nothing but length, height, breadth. So you can integrate it by this equation by 3 times. You get the form factor value. That is the form factor value calculation. This value E can be calculated by using Fourier transformation. By using Fourier transformation. Each and everyone knows Fourier transformation. This Fourier transformation is occurred in MMP, Mathematical Methods of Physics, transformation, Laplace transformation, Fourier transformation, integral transformation. Number of transformations are occurred in numerical methods and MMP, particularly MMP paper, numerical methods point of view, number of transformations are occurred. Particularly, this equation can be solved by Fourier. Fourier transformations method. Fourier transformation method of electron density. That equation can be solved by using Fourier transformation method. According to Fourier transformation method, we get e power I into delta k bar I bar can be represented by summation of 2l plus 1 into I dash JL into delta KR into PL into cos theta at delta KL. This is from L tends to 0 to infinite. L tends to 0 to infinite. That is Fourier transformation. From Fourier transformation, electron density can be written as e power I into delta KR. This value can be represented by like this. Here PL, particularly here PL. What is PL? PL is nothing but Lagrange. PL is nothing but Lagrange polynomial. Lagrange polynomial of order L, and delta theta delta KL is nothing but angle between delta K bar and R bar, and J suffix L is nothing but spherical Bessel's function. Based on this Fourier transformation, by using Fourier transformation, exponential of I into delta KR can be represented as summation of 2L plus 1 into I dash JL delta KR PL into cos theta. What is PL? PL is nothing but Lagrange polynomial of order L, and delta theta can be nothing but angle between delta k and r bar. Delta k already you can draw in the diagram. Incident ray or diffracted ray, and r is the at what point you can measure the x-rays, the two angles. JL is nothing but spherical Bessel's function. Based on this Fourier transformation, you can substitute in that equation. You get the form factor value. F is equal to, here integration is occurred with respect to volume. Volume is nothing but 3 integrals. So triple integral of sigma r into sine delta kr divided by delta kr into r square dr sine theta into d theta into d phi. Here angle integration, some pi is equal to 0 to 2 pi, theta can be taken as 0 to pi, and r value can be taken as 0 to infinity. That is your form factor value. Form factor value is equal to triple integral of integral sigma r into sine delta kr by delta kr, r square into dr into sine theta into d theta into d phi. Here d phi is nothing but phase angle, theta is nothing but angle between delta k and r is nothing but position vector. So you can integrating this equation by with respect to phi. First of all, after getting the result, you can integrate the with respect to angle. After calculation that part, finally we can integrate with respect to position vector. So on completion of these 3 integral values, finally you get the form factor value. On integrating, you can integrating this equation, we get on integrating is nothing but P naught of cos theta value approximately equal to 1 and J naught into delta kr value approximately equal to sine delta kr by delta kr. On integrating, we get the result. So these values can be substituted in this equation. Finally you get the result is form factor F is equal to 4 pi into single integral of 0 to infinity, nothing but r value. This is r is equal to 0 to infinity. So pi value theta on integrating we get 4 pi into integral of rho of r into sine delta kr by delta kr, sine delta kr by delta kr into r square into dr. So you can calculating the 2 integral, finally you get the form factor value is F is equal to 4 pi into integral 0 to infinity rho of r into sine delta r by delta kr into r square into dr. If theta tends to 0, sine of delta kr by delta kr value approximately equal to 1. These two values can be substituted in the above equation. You get the form factor value. F is equal to 4 pi into integral 0 to infinity rho of r into sine delta kr by kr value is equal to 1. So you get r square into dr. This is the form factor value. So form factor value on calculating, we get the result is F is equal to 4 pi into integral 0 to infinity rho of r into r square into dr. If rho of r is can be constant, integration of r square into dr value is r cube by 3. R value 0 to infinity. You can substitute r is equal to 0, 0. Infinity is nothing but large value. So on. You can take the atoms in the crystal, particularly already we are mentioned the atoms must be taken as very small in size. Particularly you can consider atoms must be considered small in size. Atoms must be considered small in size. Small in size nothing but you can consider the atoms in point size. So for point size atoms are considered this F value is nothing but form factor value. You get the result is F is equal to 4 pi into integral 0 to infinity rho of r into r square into dr value must be equal to Z. What is Z? Z is nothing but atomic number. Particularly the atoms must be considered in point size. This efficiency of scattered X-rays can be a value of form factor value must be equal to atomic number of the element or atom. So on calculating particularly this term particularly used, the atoms must be in small in size. This is the calculation of form factor value. This is the calculation of form factor value. So the atoms must be taken into point sized atoms. The form factor value must be equal to atomic number. So this is the form factor value calculation. Why you are calculating the form factor value? This form factor value calculation gives the efficiency, which gives the efficiency of scattered X-rays. Efficiency of the scattered X-rays of the atoms. X-rays of the atoms. So, which is nothing but measure, which gives the measurement, of efficiency on that way. So, at what condition diffraction is occurs? How much amount of rays are diffracted? That how much amount of X-rays are diffracted can be explained based on this form factor value. Particularly this form factor value calculation point of view, finally you get the result by based on or assumed the atoms must be in small in size. You can consider the small in size. This form factor value must be equal to atomic number of the atom or element. Atomic number of the atom or particularly at that element. So F value must be equal to Z. So you can consider the lattice planes. So this is the point sized atoms. Here I am showing the totally 10 atoms. I am inserting on the X-rays like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All X-rays are diffracted like this. So, based on this form factor value, the diffracted X-rays were, the diffracted X-rays means, diffraction must be taken as complete or total diffraction by all atoms in the given crystal. So According to form factor value, you can determine the efficiency of the scattered rays. This efficiency of the scattered rays must be taken into all atoms of diffraction occurred in the crystal. So here I am taking 10 atoms are existed. You can take the scattered rays by 10 atoms. The total diffraction can be explained by the form factor value. So this can be explained by the in unit cell. You can explain the unit cell. That combination of unit cell is nothing but a crystal. So the diffraction of atoms completely taken by the unit cell gives the efficiency of the scattered rays. That efficiency of the scattered rays is explained by form factor value. That is form factor value. Based on each atom in the crystal. The amplitude of the scattered X-rays always be proportional to the value of form factor or atomic scattering factor. So the amplitude of the scattering A value is always be proportional to F. Already we are explained intensity value is directly proportional to square of the amplitude. So intensity of diffracted X-rays is always be proportional to F square value. What is F? Form factor value. Once your form factor value is calculated, the square of the form factor is nothing but intensity of X-rays. Intensity of X-rays or intensity of diffracted X-rays. So the diffracted X-rays can be based on this form factor value. Square of the form factor value is nothing but intensity of diffracted X-rays. Particularly which is dependent on position of the atoms in the unit cell. Position of the atom in the unit cell. So this intensity of diffracted rays must be depending on position of the atom. Why you are using the position of the atom? Suppose you can consider the lattice plane. This is the point-sized atoms. You can insert the X-ray like this in between the lattice point. Here in this condition diffraction is occurs or not, we don't know. Because here 2D sin theta is equal to L lambda. This condition is obeys at a particular incident wavelength lambda at a particular glancing angle theta. Based on these two, diffraction pattern is obeys or not, we don't know to explain it. So particular at this position, you can incident on the X-ray on the atom. At this condition, diffraction is must occurs. That must occurs condition. So the intensity of diffracted rays must be depending on position of the atoms in the unit cell. So the form factor can be explained with respect to position of the atoms. So the form factor value mainly depending on position of the atom. In this way you can calculate the form factor value. So it is a very lengthy derivation. So after that some more derivation is existed which can be discussed in next class. So this is the value to calculate the form factor. Why you are calculating form factor? By calculating the form factor, you can easily explain the efficiency of the scattered rays on the atoms. Efficiency of the scattered rays. How much amount of X-rays are diffracted. That how much amount can be explained by using this form factor value. Intensity value is always be directly proportional to square of the amplitude. Amplitude of the scattered X-rays is always be proportional to value of the form factor. So I is proportional to A square means I is proportional to F square. I is nothing but intensity of scattered X-rays is always be directly proportional to square of the value of the form factor. So the intensity of the diffracted values can be explained practically based on form factor value. So form factor value definition is which is the measure of efficiency of the X-rays to be diffracted. X-rays to be diffracted. Otherwise, and more definition is there. Form factor or atomic scattering factor value mainly defined as the ratio of amplitude of the X-rays with respect to atom to electron beam. So the ratio of amplitude of scattered X-rays by the atom to the amplitude of the scattered X-rays by the electron. That is the definition of form factor. So form factor has no units and no dimensional path law. Finally you get amplitude of the X-rays, scattered X-rays is directly proportional to form factor value. This amplitude square is directly proportional to intensity. So intensity of diffracted X-rays is directly proportional to square of the amplitude. In this way you can calculate the form factor value. Remaining derivation we can discuss it in next class. Okay? Clearly follow the derivation. Each and every step you can follow it. Okay?